Before we dive into fluorine, let's first take a moment to clarify the differences between fluorine, fluoride, and fluorite, because these three are often confused, yet each represents something quite distinct. Fluorine, fluoride, and fluorite differ fundamentally in form and behavior. Fluorine is a highly reactive and toxic gas, rarely found freely in nature due to its extreme chemical activity. Fluoride, by contrast, is the stable ionic form that results when fluorine gains an electron. It is commonly found in compounds and is safe in controlled amounts, such as in dental care products and treated water. Fluorite is a naturally occurring solid mineral composed of calcium and fluoride ions, serving as the primary industrial source of fluorine and widely used in metallurgy and manufacturing. In essence, fluorine is the reactive element, fluoride is its stable ionic form, and fluorite is the mineral that contains it. With this distinction in mind, we can now begin to explore fluorine itself. Fluorine is one of the most reactive elements in the periodic table. It is known for its ability to bond quickly and powerfully with other elements. Because of this, fluorine almost never exists on its own in nature. Instead, it appears in compounds, forms that we interact with every day, often without even realizing it. In its essence, fluorine represents a force that can penetrate, transform, and connect. This same property that makes it highly reactive also makes it incredibly useful in both daily life and advanced technology. Let's start with something very familiar, your bathroom. Fluoride, which is a compound containing fluorine, is commonly found in toothpaste and sometimes in drinking water. In small amounts, it helps strengthen your teeth and protects against decay. It integrates into the enamel, making it more resistant to damage. Here, fluorine becomes protective. It supports structure and long-term stability. But this already shows an important principle: balance. In low doses, fluoride protects. In high doses, it can become harmful. This dual nature is a key characteristic of fluorine. It exists at the boundary between benefit and risk. Now move into your kitchen. If you use non-stick cookware, such as Teflon-coated pans, you are using fluorine-based materials. These coatings are made from fluoropolymers, which are extremely stable and resistant. Nothing sticks to them. Heat does not easily damage them. Chemicals do not easily break them down. In this form, fluorine becomes durability and resistance. Then think about your home environment. Air conditioners and refrigerators rely on fluorinated gases to cool spaces and preserve food. Without these compounds, modern cooling systems would not exist as we know them. Fluorine here enables comfort, preservation, and control of temperature in everyday life. Fluorine is also present in clothing and materials. Many water-resistant jackets, stain-resistant fabrics, and protective coatings use fluorinated compounds. They create barriers against water and dirt. Again, fluorine acts as a protector, forming invisible shields. Now, let's go deeper into technology. Fluorine plays a crucial role in electronics and industry. Hydrofluoric acid, a compound of fluorine, is used to etch glass and manufacture microchips. It can cut and shape materials at the microscopic level with extreme precision. This makes it essential in producing modern electronics, including the devices we use every day. Fluorine is also widely used in medicine. Many pharmaceutical drugs include fluorine atoms because they help stabilize molecules and improve their effectiveness in the body. Here, fluorine becomes a tool for healing and optimization. Moving further into advanced technology and space, fluorine-based materials are used in aerospace engineering. They are found in insulation, coatings, and components that must withstand extreme heat, radiation, and chemical exposure. Satellites, spacecraft, and high-performance systems rely on these materials because they remain stable under conditions where most substances would fail. Fluorine has even been studied for use in rocket propulsion due to its extreme reactivity. While it is rarely used directly because of its danger, its potential shows just how powerful this element is. Now, let's return to nature. Fluorine appears naturally in a mineral called fluorite. Fluorite forms beautiful crystals, often in shades of purple, green, or blue. In this form, the intense reactivity of fluorine is stabilized within a structured lattice. What is aggressive in its pure state becomes ordered and harmonious. Fluorine is also present in small amounts in oceans and water systems, and in the human body in bones and teeth, where it contributes to structural strength. So when we look at fluorine across all these levels, a pattern emerges. In its raw form, it is highly reactive, capable of breaking through barriers and initiating change. In minerals like fluorite, it becomes stable and structured. As fluoride, it becomes protective, supporting health in controlled doses. In materials and technology, it becomes versatile, resistant, and precise. And in advanced systems, it enables innovation and performance under extreme conditions. Fluorine teaches us something fundamental. Transformation depends on form and balance. The same element can be aggressive or protective, destructive or supportive, depending on how it is integrated. Understanding fluorine is not just about chemistry. It is about recognizing how powerful forces, when guided and structured, can become essential parts of both nature and human life.